Hey there, Math 126 fans. Going to continue and talk about double integrals. This is basically sections 15.1 and 15.2 of Math 126. And it's really about understanding how to describe a region. So it's actually a Math 125 skill. Now, in my experience, it is a Math 125 skill that students struggle with. And so just wrong click. Just a moment here. So I really encourage you to do 15.2, this region practice. In particular, I think this sheet would be helpful if you can't quite remember how these things go in Math 125, which is basically how would you draw those? How would you describe the region? I have full solutions to this. How do you switch the order? I'm going to do some of that in this video as well, but I have a lot of other resources if you need more practice. Okay, so given a problem, your first step is to draw this. Now I'm going to draw it twice. You don't need to draw it twice, but I'm going to draw it twice for explanation reasons. Okay, so I'm going to draw y equals the square root of x. Okay, that's that. Y equals the square root of x. Okay, that's that. I'm going to draw y equals 2, all the points where y is 2. That's up here. That's up here. And x equals 0. That's this side. Okay, there's the region. Now in these problems, you have to remember, because I find sometimes students forget this, you have a region on the ground, and then completely separate from that, you have a surface, and we're trying to find the volume between them. They already told us the surface. It's z equals e to the y to the third. Okay, now here's what I tell people in Math 125, and it's the same thing I say in Math 126, which is you have to decide whether you want to do everything in terms of x or y. So really this is about labeling. So consider this region between them. Let's label x just to try it. If you're talking about x, you're between blue and whatever that is, red. You would need to label everything in terms of x. Alternatively, you could try to label everything in terms of y. So try to draw a particular example and then work from that. So now we're just going to do some labeling. I do a lot of this in Math 125. So how far is it from here to here? You should know that's what the function is. It's y equals the square root of x. In fact, you could even label that point and say if you labeled this xy, the y would be square root of x. And then I always think about this like mowing the lawn. What if you had to mow the lawn and someone said you had to do it this way? When would you turn the mower on and when would you turn it off? You would turn it on when you got to the square root of whatever your x is, and you would turn it off when you got to y equals 2. So it's really labeling. But how then would the person know to stop? Well, they would stop when they get to this intersection. They would start here. So I sometimes jokingly say, if I start walking this way, tell me when I hit the region. And I make students hit the buzzer. I slide my hand across and we go, 0. That's the smallest x can be. What's the biggest that x could have been? Well, it's right there. So we need to do some solving. If y is 2, what's x? Oh, it's 4. So one way to describe this is for every x between 0 and 4, and that's what I mean when I say I'm doing it in terms of x, there is a pattern for how far we go. And that pattern is we're going to go from the square root of x to 2. And that's how these iterated integrals work. And then in here you have e to the y cubed. That's one way to set up the problem. At any point in time, you can check your work as follows. Just pick some random numbers between 0 and 4 and plug them in here. So for example, if I plug in a 1, is 1 smaller than 2? Yes. Does it give me a reasonable range? 1 to 2, yes. So that's always a quick check. If a variable escapes, there's something gone wrong. Meaning if there's a y here and this is dy, something went terribly wrong. Because once you are done integrating this, the only thing that should be left is x. Okay, that's what we mean we're doing it in terms of x. Okay, just for the practice, let's talk about in terms of y. What if I want to mow the yard this way? And I want to walk on every single blade of grass. Well, the smallest y can be is 0. The biggest y can be is 2. So here's an equivalent way to set this up. 0 to 2, dy. And then based off of y, it's important we get this ordering right. Based off of y, what's the biggest and smallest? So we need to label these points. So based off of y, what is x? Based off of y, what is x? Now this x is always 0. It's the left side. That x we got to rearrange, right? Because it's not in the form we want. I can't say square root of x. That doesn't make sense because I'm giving you a y. So we have to say x is y squared. Now, occasionally, sometimes students have trouble seeing which one is bigger, but hopefully you see that 0 is smaller than y squared. So you write the integral from 0 to y squared. And that's really just describing the region. That you did the same things in Math 125. It's just you did something different with them. You did top minus bottom or left minus right. So there is the process. So I really like this. I think it is challenging for students at first, but if you can organize your thinking, draw the regions, label x or y, then you're set to go. Now in this particular case, I don't know how to integrate this. I can't think of a way because there's no y squared outside. So we're out of luck there. So we have to do it the other way. So that was kind of the challenge of this question, is you couldn't do that. In terms of integrating, this we can do because I erased the one that we can do. So people are yelling at me. This should be dx. So this is the one we can't do because I don't know how to integrate with respect to y. I do know how to integrate this with respect to x because this is just like a constant. So you'd have e to the y cubed x evaluated from x equals 0 to y squared. And that one we can do. It just means that we're better cross sections that way. So it's going to be y squared. Better in the sense that we could integrate to get them. Just a second, zoom out a little bit. And then you keep going. So I think I'm going to stop there. This, if you want to see the full solution, this is my spring 2019 exam in my exam archive. Just briefly, I don't have the visual for this question ready, but I thought I would show a separate visual just of a different problem. So what we're doing when I say we're describing, so here's a surface, here's a region on the ground. This is an example I always do in lecture. Let's remove the surface for a second and just talk about describing the region. So you can do it in terms of, in terms of y or in terms of x. Zoom out a little bit. So here's the x-axis, here's the y-axis. So if you do it in terms of y, which is what I have right now, it's going to look like this. That's how I walk through all the points. And we're basically finding the area of each of those and adding them up. So the inner integral represents the area of that. So if you plug in a particular value, compute the inner integral, it'll tell you the area of that triangle. Okay? We can also do it in terms of x. Now in terms of x, it's totally different. It's a different cross section, but it's going to give us the same volume because they're rectangles. You can see that. So in order to do that, you have to be able to describe what the top and bottom are, or what the left and right are. That's all we're doing really, is we're finding those areas. Now in the next section, when you get to polar, we give a third option, which is to think of it in a polar way, like a radar screen. And we talk about some of the adjustments you have to make. And that's basically the quick version of chapter 15, is learning several ways to describe regions and then using those descriptions to help us do volume and a few applications. Okay, so let's circle back and try another one. This is from another one of my old exams. Let me look here and see if I can spot it, which one it was. Nope. I think this is spring 23. Let me just get it right. Yes. Okay, so here's an example of one where when I look at it, it sort of screams at me which variable to use. And the reason, this is the same thing I talk about in Math 125. In Math 125, I often put up a bunch of graphs and I say X or Y, X or Y, X or Y. And you can do that right here. X or Y. And we should immediately know, because if I start walking this way and do things in terms of x, the pattern will be different if x is here or it's here. You can see that. It's yellow on the bottom here and green on the bottom here. Because of that, I don't want to do it in terms of x, because it doesn't mean you can't do it, but I would have to change my description. I'd have to change how to mow the yard when I get past this little intersection. So that tells me I would much rather use y. So now I label y. Because if I label y, I'm only between these two colors. That's it. the same thing we said in Math 125. Okay, so this is y, and I want to describe where to start and stop. Okay, so we have a little bit of work to do, an intersection to do, so maybe I'll say something briefly about this, because I really need to know where we start and end. Let's substitute y is equal to y squared minus 2. We get 0 is y squared minus. So this is just me trying to get the intersections. I assume it factors, let's see, minus 2 plus 1. So they intersect at 2. Okay, so I can see in the picture that I want to do in terms of y, and y could be anything from 0 to 2. Now, I need to describe how far it is to enter the region and how far it is to exit the region. In other words, I need to know what those are in terms of y. So which one is the line? That's this one. In terms of y, that's x equals y plus 2. Is that the bigger x value or the smaller? You should see it's the bigger. So that's going to be my y plus 2. Okay, what about the smaller? Well, that's going to be this equation in terms of y, so it's y squared. So that's it, and then you evaluate. If you want to check my notes, you can do it in terms of x. Sometimes I do this in my solutions, I actually do it in terms of x as well. But if you want to do it in terms of x, you have some more work to do. So let me just quickly label a few things. You could have to go through and solve those, and then you'd have to break it up into 2 problems. You would say, okay, so here's the other way of doing this problem, the bad way in my opinion. From 0 to 2, you would have one pattern. And basically you'd be finding the volume above this. And then separately, you'd add the area above 2 and 4. And you'd have a different pattern there. What are those patterns? From 0 to 2, the bottom is 0, and the top is the square root of x. I'm just taking that and solving. And this would be 2y dy. When you're over here, the bottom is the line, x minus 2. The top is the square root of x. Both of these are correct. You could compute both of those integrals separately, add them together, and you're going to get the answer, which is 16/3 all together. Or you could just do this single integral, and you're also going to get 16/3. So that's the point. Part of what you're learning in that section is giving you flexibility to choose an efficient computational path. Okay. So if you're having trouble with that labeling, which a lot of students do, check out my review resources. Let's do a couple other types of problems. So this reversing the order is one I always get asked about a lot. I think there's an uneasiness about it. The issue isn't about calculus, it's about drawing a region. So this is asking you to draw the region. I know it doesn't say that, but you need to draw the region to successfully do these problems. Maybe sometimes you can get lucky, but in general, you need to draw the region. Okay, so we need to say this is all in terms of x, sort of rethink the process. So there's 2 bits of advice when I see this. I always immediately write, all right, we're talking about x is between 0 and 2, and I think of those as tick marks. That's what I tell students how to think about it. That's the starting and ending. Those aren't necessarily curves. Think back to this example we just did. Was x equals 4 a curve? No, it was just where we started. So in your head, you should think about those as tick marks on the x-axis. So the outer bounds are just starting and ending tick marks. Don't actually draw a line there. At least not yet. And then the inner bounds tell you the actual functions. 8x and 2x cubed. So the other thing I need to graph is 8x, which we should know is a line, and 2x cubed, which we should know is a cubic. Okay, so y equals 8x, that looks like some steep line. And then I need to draw a cubic. Doesn't have to be perfect. I think when you plug in 2 to both, you get 16. Oh yeah, so I did plug in 2 and 0 so that I could make a somewhat accurate graph. But all you need your graph to do is have the appropriate relationships. Which one's bigger, which one's smaller. Okay, now that we have the picture, we just do the analysis again, but we do it in terms of y. Okay, so let's erase this and rethink the problem. in terms of y, so if I pick a random y here, first, what's the biggest and smallest y can be? The smallest is 0. The biggest is wherever those two things intersect. I should have found that before I erased. But when do these two things intersect? When is 8x equal to 2x cubed? Actually, they intersect at 2. So I should already be plugging that in. It's just 16. Both of them give me 16. So from 0 to 16, let's mow the yard this way. But I need to know when to turn the mower on and when to turn it off. I turn it on when I get to this line, y equals 8x. I turn it off when I get to this cubic. So now I need to integrate. They don't tell me what the function is. This is just a question about changing the bounds. I'm doing it in terms of y. Okay, so I need to label where that is and where that is, but I need to label it in terms of y. So I need to rearrange. The lower bound is y over 8. By lower, it means smaller distance to walk. And the upper bound is over here, which I need to solve. So y over 2 is x cubed. So this is going to be y over 2 to the 1/3. Done. Lots of places you can practice that, but you can see my number one thought process is draw the region, draw the region, draw the region, draw the region. Okay. Let's move this down a little bit. Well, won't let me do it. Okay, so this gets faster and faster the more you do these sorts of problems. There we go. So let's look at another one from one of my old exams. So it says, just draw the region and reverse the order. So the tick marks are x equals 0 to 2. Oh, that just happens to be the same as the last one. So you go 0, you go 2. Then you draw the parabola, y equals x squared. Success. And then you draw y equals 4. So the things you should draw, some quick tips, is draw the inside. These curves you will draw. These you won't draw. You just put them as tick marks. That's important because otherwise you might get the wrong thing shaded. So it needs to be between y equals 4 and y equals x squared. That means it's up here. As opposed, a lot of times what happens is people draw lines for all these and then they just guess at which one to shade, but that totally throws you off. So now we want to do it in terms of y. What's the biggest and smallest y can be? It's 0 to 4. Now, in terms of y, what's the biggest and smallest x can be? So I need to describe these points. What is this x? And what is this x in terms of y? Well, the lower one is 0. The upper one is whatever this is when I solve for x in terms of y. So it's the square root of y. X sine of y squared. So you can see the goal is to take this, turn it into a picture, give the new bounds. That's what the goal of these is about. Okay, let's try another one. A lot of students asked me about this, so I just thought, hey, I can do a whole bunch of these. These don't take long. So they give me this double integral. It says reverse the order. These are tick marks. These are the curves that tell me when to turn my mower on and off. So right away you would have tick marks at y equals 0 and y equals 2. Again, these are talking about y. And then you would also need to graph x equals 4 and x equals 2y. Those are the inner bounds. X equals 4 is right here. Done. This, in my head, I feel like I want to write, for some reason, 1/2 x. And I'm like, oh yeah, this is a line with slope of half. Now, what do we shade? And this is why I say tick mark so much, because what I'll see students do is they'll draw this line and then they have no idea what to shade. So the outer bounds, don't put a line there, just put a tick mark. I hope that kind of helps you a little bit. And now what are we trying to do? We don't want to do it in terms of y. We want to do it in terms of x. So we label this x. We label those 2 points. And then we're off to the races. The smallest x can be is 0. The biggest x can be is 4. Dx. Based off of x, what's the biggest and smallest y can be? The inside is unchanged. smallest y can be as 0. The biggest y can be as 1/2 x. Done. So there's several reverse the order questions. You can find many, many more on the homework and in my practice materials. Lastly, let's finish with some applied questions here. So find the volume. This always scares people because it's so many equations. This is from, just going to look here real quick to see if I see where it's from. Yeah, this one's from my spring 2019 exam if you want to try it out on your own. Find the volume of the, you can just pause. Find the volume of the solid in the first octant. That just means x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0. Bounded by the parabolic cylinder, well, that sounds scary, and the plane y equals 3. So a process to do any such problem is to look for your z's right there. Now, in Math 224, we talk about, well, what if you want to try to do it in terms of another variable? But we leave that for Math 224. Everything we do in this course, we have it in terms of z. There are two z's in this problem, z equals 0 and z equals this. Those are the only things that describe height. So I always tell students, that's your integrand. That's what you're going to put here. Then the rest of your job, you could also do the 0, but it's going to be nothing. The rest of your job is to draw the region on the ground. So here was step 1, integrand. Done. All we had to do is find the z. Step 2, draw the region on the ground. That often involves doing a couple things. So let's talk about those couple things. Are there any given x, y restrictions or curves? Equations that only have x and y in them. Yeah, there are 3. There's x equals 0, there's y equals 0 because it's first octant, and there's y equals 3. Graph those 3 things. I'm not going to do anything with this yet because that has a z in it. Okay, so y equals 3 is here. We have x equals 0 is here. And we have y equals 0 is here. That doesn't quite make sense. So this happens sometimes. Either the question is mistakenly written or there's something else going on. And this always confuses students just because it's a little harder to visualize in 3D. But you know this already. Like sometimes when we were finding the area under a curve, we gave you the bounds. And sometimes you had to find the bounds by doing an intersection, right? Same thing's going on here, except it's for surfaces. So it's always this issue of getting kind of lost in the fact that you have a region on the ground. Let me sort of draw it here. And you have a surface up here. Now the surface might actually hit the ground, and in this case it does, in which case that provides another boundary. So you don't have to think about it. You just graph the given xy curves, and you have one other question, which is, do the z's intersect? And in this case, they do. The two z's in the problem are z equals 0 for the ground and this. Do these two things intersect? They do. They intersect when 12 minus 3x squared is 0. So when 12 is equal to 3x squared. So when x squared equals 4. And so when x is equal to plus or minus 2. But since we're in the first octant, it's just the plus. You also graph that, which is right here. And that completes the picture. If in fact I was going to graph this, here's what it looks like. And the reason we were confused is because the surface itself contributes the other boundary. And then we're finding that volume. Okay, this is a rectangular region. Mostly I just want to talk about that piece. Integrand, draw the given xy curves. Sometimes that tells you all the bounds you need. Intersect your z's. Sometimes that contributes another bound. And then you're ready to integrate. You can do it in terms of x or in terms of y, it doesn't matter. Let's say we do it in terms of x. X goes from 0 to 2. Based off of x, y goes from 0 to 3. And it's 12 minus 3x squared dy. And I do that in my notes. It comes out to be 48. Again, this is my spring 2019 exam if you want to try it. But I just want to talk about that process. Let's do it again. Find the volume under the plane, and I think this was in the homework, above z equals 0 and enclosed by this. Let's follow the process. Are there any z's? There and there. Those are the only things in this problem that describe height. This one becomes, if I solve for z, it becomes z equals 8x plus 2y. So there's our z's. We're doing the volume between those. And so we write the double integral of 8x plus 2y. Step 1 done. Step 2. Are there any given xy equations? Yeah, there are. There are 3. 1, 2, 3. I need to graph those now. So now I'm going to start to try to draw the region. That will involve me drawing y equals x. Done. Actually, that looks like y equals 2x. And then I need to draw y equals x. And then I need to draw y equals 2. Now, where would y equals 2 be? It's going to be going this way. Ah. So it's this region. And then we've landed in a situation where we have to think, would we rather do it in terms of x or do it in terms of y? That really doesn't have to do with the setup. It just has to do with the region. The region chooses the variable. I do not want to do it in terms of x because sometimes it's blue to pink and sometimes it's blue to yellow. So I'd have to change the way I mow the yard. But if I do it in terms of y, I don't have a change. Okay, so I would like to do it in terms of y. Notice that graphing the given was enough. I didn't need to do the intersection of the z's. If you wanted to, you could. That would tell you when the surface hits the ground, but it hits outside this region, so that's why it wasn't needed. Okay, so y could be anything from 0 to 2 dy. I have this integrand, 8x plus 2y, and now I just need to figure out how far over to go. What is that dot and that dot in terms of y? I'm trying to figure out how far over to walk. So the bigger one is x equals y. The smaller one is x equals y over 2. And then we can compute. What was this from? Yeah, this was my fall 2018 question 2A. Plenty more examples like this you can find on my page, but I hope that gives you a thought process basically for those double integral problems. How do we approach? So it's all about describing regions. It's those 125 skills. I talked a bit about reversing the order. I talked a bit about setup. All right, hope that's helpful.